Hello guys, today I'm going to teach you about what is optimal binary search tree and what is the use of it. Okay, and how do we construct the optimal binary search tree. Before going to our explanation of the optimal binary search tree, let us understand what is the binary search tree. We know that, let's say there is one root node in the tree, that all the left subtrees of that particular node that contains the lesser value than the particular parent node, and which is in our case which is a root node, and similarly for the right subtree that contains the higher value than the root node or say parent node. So basically in the binary search tree, if there is a particular node over there and it has left subtree and the right subtree, then all nodes in the left subtree has the key values which are the lesser than the parent node, and all the nodes in the right subtree which has the higher value than the parent node's key. Basically in all our scenarios we only know the key values of each node, that what is the key of that node. But let's say now we also know the frequencies of each node. Okay, and the frequencies that come in the scenario of the searching. The frequencies are comes in the scenario of searching. Or what do we mean by searching here? Let's say we are searching some of the nodes in the tree, and the number of times they are appearing or they are being searched, that is called as the frequencies. Okay, so by knowing the frequencies of each node and the key values, we can find the overall cost of the searching. The overall cost of the searching here is that for all nodes we know the frequencies of that node and we also know the key values of that node, and by knowing the key values we can construct our binary search tree, and by knowing the frequencies of that node we can also find the overall cost of the searching. Okay, and I'm going to explain that how do we find the overall cost of the searching in later now in we this are video. Going in the some another way of our topic, which is says that the overall search time. Okay, by comparing the binary search tree, which is the unbalanced binary search tree, and the balanced binary search tree. Okay, we know that the balanced binary search tree has the less search time than the binary search tree. Why it is so? Because the balanced binary search tree has the less number of levels. Why it has the less number of levels? Oh, for that, let's say if there is a root node and it has the left part of the binary search tree and the right part of the binary search tree. In the case of the balanced binary search tree, the left part and the right part of the root node, or say the left part and the right part of the parent node, has the only difference of plus or minus 1 only. So that both the right part and the left part are closely similar. So it has the number of levels are less, in which is not the case in the binary search tree, which is unbalanced. So it has the more number of levels, so the search time is more. So it is not only that the balanced binary search tree has the least search time, there is another one method which can further reduce the cost of the balanced binary search tree, and which is the optimal binary search tree. So we can say that by using the optimal binary search tree, we can determine what is the least searching time of our binary search tree. Let us understand that how the optimal binary search tree has the least time than the balanced binary search tree. We have the example that there are three nodes, that is node with the key value 20, 30 and 60, and the frequencies are likewise 2, 1 and 6. So we can say that the frequency which has the 6 frequency, that it is appeared the 6 times in the searching process, and that of the which has the frequency of 2, that appears 2 times, and the 1 has appears 1 time. So the key which has the value of 40, that has the frequency 6, that is appearing most of the time in among these three. So by using these three nodes and the various keys, we can construct various 5 binary search trees. Various 5 binary search trees. So how it is so? How we can construct the binary search tree, and how we can know that how many binary search trees are possible. So for that there is one formula which is used. So the formula says that it has the various 2ncn upon n plus 1 different binary search trees, where n are the number of nodes. So In our case, which is 3, so we have to put only the value of n equal to 3 in that formula, and you can verify that the number will be appear like 5. So there are various 5 binary search trees I have constructed. We can see here that in the first binary search tree that the number this is 1, 2 and 3, which indicates the level, so that the node which have the key value 20 appears at 1 level, first level, which is the 30 has in second level, and the 40 has third level. We know that the node which has the key value 20 has the frequency of 2, 30 has the frequency of 1, and the 40 has the frequency of 6. So how we can find the overall searching cost? So we have to multiply the node's level, so at which level it node is appears, and with that of the frequency of that particular node. So let's say for first binary search tree, this is 1, which indicates that the level of 20, and the which is 2, which has the frequency of 20. So the 20 has the frequency of 2, the 30 has the frequency of 1, and 40 has the frequency of 6. So 2 into 1, which is 30, appears at level 2 and has the frequency of 1, and the 40 appears at level 3 and the frequency of 6. So we have to add them all. We can get that the overall cost here is 22, and so for the case for everyone, so has the cost of 17, 17, 13 and 14. So here I have written that the cost is computed by the multiplying the each node's frequencies with the level of the tree. So here that the frequency and the level, the first indicates the level and the second indicates the frequencies. We have to multiply them all, and then we have to add that. So we can construct the 5 various binary search tree, and we have determined all the cost of that searching times. Okay, now we have to compare these things. As we can see in figure 2, so consider this binary search tree and this binary search tree, which is figure 4. There are 5 various types of arrangements, and as we can see that it is possible to further reduce the cost of the balanced binary search tree, and which is specified in the following figure. So we can see here that the second binary search tree, which is the balanced binary search tree, which that this is the root node, it